We're very fortunate to have Emily Zoom in with us today. Emily is a research professor at Duke University, and she is the head of the National Q12 Partnership. So she is very active in advocating for quantum education nationally. And so she is with us today to share some resources from her partnership. And so I'm going to put Emily on now. Thank you.
Sorry, I'm not there with you. I would love to be there, and I hope if you have questions about this or stuff that Chandralekha, who will talk next, has, then our colleague Jen Palmer is there in the room, and we'll hopefully be able to chat. And you can also reach out to any of us anytime about this. So first, I should say, happy International Year of Quantum Science and Technology. I also am on that a steering committee for that. So if you want to chat about that anytime, please also reach out. So I was asked to talk a little bit about the National Q12 Education Partnership, and specifically about like sort of its genesis and resources for instruction. So I just want to quickly start my timer so I don't go over time. So let me just, okay, there we go. Oh, and so this work is funded by the National Science Foundation and the Army Research Office through the Laboratory of Physical Sciences. So it's a federally funded program. We do also get a little bit of support from industry, and then some other in-kind efforts. So I know you've heard a lot already, but I just wanted to say, I love quantum, and when I talk about it, I really think about, I used to do atomic physics, so I really think about things that are really small or really cold, near absolute zero, or both, as the place that, practically we think about quantum information. I will also say, though, that, obviously quantum mechanics is a theory in physics by which we understand nature broadly, and it's not just restricted to quantum information. But in the 21st century, and I think Chandralekha will talk a little bit about this, quantum information science is more than just the physics that we've, more than just physics, more than just trying to understand nature at fundamental scales. It's about controlling purely quantum features to improve technology, do science, and solve problems for humanity. So it's a big statement of what it can do. And perhaps that's just a physics perspective, but I do think it is more than physics, and it is cross-disciplinary at this stage. And recognizing this from a policy perspective, there was the National Quantum Initiative Act that was signed in 2018 that was previously mentioned. And in the recognition that we needed to develop a broader, multidisciplinary, diverse workforce, there's language in the Act that articulates the need for this pipeline and the need for curricula. Originally, there was no mention of K through 12 education, actually, but there was mention of public outreach. But I think there was a recognition pretty early on that there was energy and excitement to bring this to younger ages, and really a necessity, because when we talk about the workforce pipeline, we're really talking about education and how can the federal investments support local implementation and support states to do what they need to bring this to students in their regions. So there was a flurry of programs that were initiated along these lines from K through graduate school that really try to target different parts of this pipeline and develop on-ramps. The K through 12 stuff didn't start right away, but there were workshops and other activities that showed that people really wanted to get involved in this. In fact, the program, Angela's program, was one of the programs that were funded under this act. And the Q12 was really developed to support the larger ecosystem. So really just trying to build the community and try to, because there are very few people who have worked in quantum education, and it's a pretty young area, trying to make sure that folks in New York are connected to folks in Illinois or people in Alabama or people in California or Colorado or New Mexico or Pennsylvania, wherever. We wanted to make sure that teachers could do what they wanted to do in their area, but also be connected to a larger ecosystem, since there were very few people in the beginning. We have more now, but it's still pretty small numbers. And so a key to achieving this is to really develop access to information, opportunity, people, and technology. And so the Q12 was established as an industry, professional society, academic partnership, but really we're really quite broad now. And this, I can't list everybody on here, but it's really anybody who is involved in K-12 or really K-14 quantum education is welcome into this community, and to develop their resources and leverage each other's resources and figure out how to move this forward in a way that doesn't leave people behind and doesn't leave members of the future workforce out of the decision making, out of the opportunities, and out of the education. We really focus on barriers that focus on lowering the barriers for teachers and schools. And so that's why I was really excited to be a part of this discussion. And we've developed, working with teachers, we sort of asked a lot of people, well, what do you need? And we've developed some pillars of activity. And Q12, I want to just reiterate, we're really trying to provide scaffolding and fill in gaps, but we're not trying to take stuff away from different groups or efforts, but really bring people together. And so, I don't know that we'll forever need this kind of quantum education initiative, because I hope someday quantum will just be infused as part of science education, and then we won't call it quantum education anymore. It's just part of the broader set of science opportunities and learning opportunities that are available to students at the K-12 level. I'm going to go through this kind of quickly, but I'll share my slides and I'm happy to chat. But there are a number of ways that the Q12 community of across all these sectors participates and works together. It's not like everybody works together with everybody else. It's more like, well, what does this region need, and who are the partners they need, and how can we help enable that? And then how can we share out research results and educational curricula that's developed with other teachers and other school districts across the nation, so that they can support and adapt to what they need. So I will say it's a sign of the both the malleability or the, living nature of the National Quantum Initiative Act that it's amended over time. So it's not set in stone. So the original act had no K-12. And then I think a sign of the success of the investment of these programs, such as the Q12 partnership, but also the professional development programs like Angela's been involved with, the research that Chandra has done, the stuff that folks have done, across the country. There's been a large effort in Texas that moves things forward. The work of these people has made it so that policymakers make changes to the law. So the National Quantum Initiative Act was amended in 2022, I believe, to include now articulation of elementary, middle, and high school, so that people saw that really the language of the original act was incomplete and left out this K through 12 space. And so they felt the need to amend that. And then there was additional investments that were authorized. Now, some of them have not happened, and we know things are in flux, but that's not the topic of today. I will say that in spite of the fluctuations, there's still a desire to continue to renew this National Quantum Initiative Act to make sure that we continue to invest in research and education in this space as a nation, and to try to support states and school districts across the country to do what they need to do or want to do in this space. And so there is language, more in-depth language in the National Quantum Initiative Act, Reauthorization Act. And this has not been passed by Congress, but there have been efforts to try to make this happen over the last couple of years. So if you're interested to know more about this, please reach out to your local legislators as well. I think Angela knows quite a bit about this as well. So I will just talk about a couple of areas, informal education resources for this for teachers. And then Chandra Lake is going to talk more, I'm going to introduce it, but Chandra Lake is going to talk about formal classroom instruction. And so, we see the resources falling into multiple categories right now, but it like just coarsely dividing them into these two areas. So in terms of formal instruction, we heard about the curricula that was mentioned that people have been developing through the programs there. And I was really excited to hear some students and see some students were talking about the impacts and hear that it's, talking about modern physics has gotten people excited. And so what I'll say is, in terms of having quantum be part of the curricula, this is not a new idea globally. This idea, like I was skeptical at first when I heard about it in 2020 and got involved in this. I was very skeptical about this idea because I do, public engagement of physics and science communication, and I love talking to children. But I was very skeptical about the teachers having room on their plate for more topics, more, and that chasing the latest and greatest idea would be both futile and also stressful for teachers. But I actually looked, and this is not a new idea, and also it partially exists already in the US. And so that makes me feel excited. And then also teachers are really the ones leading the way on this, and educators who have knowledge in curricula. And so, I feel like our role as the Q12 is just to follow their lead and to listen to what they're saying about the importance for their students. And so in Europe, in the physics curricula, primarily, they already have quantum concepts. In the US, there are Texas standards that include quantum in the physics curricula. Virginia and Ohio has quantum in their computer science framework. So what we set out to do, and Chandra Lake will talk more about, is to figure out where quantum information science could possibly fit with the current curricula. And then from there, if there is a need for supplemental ways of putting it, not just infusing it, but having separate electives, then that could be also pursued. We've primarily focused on the infusion model at this stage, and found, and Chandra Lake will talk about this, but I'll say that the opportunities are in chemistry, math, physics, and computer science. If people have career technical education and engineering, then I think there are also opportunities there, but predominantly so far, this program has it's only a few years old, has focused on where does it fit into these areas. And I'll say that I think the area that has a lot of opportunity that hasn't been tapped into yet, and what we're seeing now, is really chemistry. But we've heard a lot about physics, and I think that's a really great place to start. It's a natural place to start. So Chandra Lake is going to talk about this, so I'm going to go pretty fast to just say that what we have is, and I think what's on your table, is a framework that is a precursor to curriculum. So the framework is to give people a starting place to have the discussion of where it fits in, so you don't have to keep going to figure this out yourselves. And so at this point, I think this framework is used by most, if not all, of the federally funded programs that do quantum education. They use it as a starting point and then adapt it. And what I'd like to emphasize is this is a draft. It's not, we didn't carve it out in stone. We just wanted to figure out where it fits in, and we want feedback from people as they go to try to develop curriculum, which I see that there's some groups doing that are actually making the lessons here at this meeting. And people, when you go to implement it, like, we want to hear feedback so that the curriculum doesn't get ossified and that it really reflects the needs of school districts, teachers, and states. The framework was created by Chandra Lake and Diana, working with teachers. So they really facilitated it working with teachers. Okay, that's all I'm going to say about it, because Chandra Lake is going to talk. In my remaining few minutes, I'm going to switch to informal learning resources and just say, if you have teachers that are like, what is available now? Now, it sounds like you have really great resources there in Long Island, and it sounds like that there's a growing movement. If there are teachers that are like, I want to do this now, and I'm a computer science teacher, or I'm a physics teacher, and I haven't done any PD yet, I don't have a course yet, I want to do this now, then we think informal activities provide a vehicle for doing this. And so what we've been trying to do is, so we developed a program called QuantTime that really focuses on collecting informal activities developed by the broader quantum education ecosystem across the country, and have those people who create them write facilitation guides that don't require teachers to know, have had a bunch of professional development. They can do this on a day before the winter break or a spring break, or they do this after an AP, or, and this can be different ages, so it's not just restricted to high school. And so this is meant to really allow people to do something now to expose their students, and to really think about, can we do activities and career days and visits and have this repertoire of exposure activities that can help people bridge a gap now to quantum in the absence of formal curricula at scale. So we run this every year. We're now running it as a regional program, so I'd love to see a program there. Where we again collect these resources. Example topics include polarization, probability. I heard probability mentioned in the last talk. Quantum computing, energy levels, superposition, where really you're using quantum concepts as a lens for students to grapple with the nature of science and the nature of technology. They get to fiddle around, they get to wonder, they get to an activity. It takes one class period and it's on some of these topics. Because I do think quantum is a really great lens by which students can learn something additional about science. And so right now, the way we work it is we work with regional leaders to figure out if they want to run Quantime, and then we try to provide support. And I will say Jen, who's in the room there, has really been a key person in this program. And so in January, the Colorado Department of Education ran Quantime for their teachers, which really just involved trying to get teachers to sign up and go to webinars and learn about quantum activities and then get to do them in their classrooms. New Mexico did a more formal thing involving a museum, and then Albuquerque Public Schools, they did that in February. And then we have people in Montana and Illinois and Indiana, Wisconsin doing this in May. So I'd love to see something in New York. It would be great. So if you're interested in this, definitely talk to Jen, and then we can make something happen. So I know I'm supposed to leave a few minutes for questions. So I'm going to talk for about a minute more and then I'm going to stop. We pair Quantime with a partner program, Quantum to Go, which is smaller scale this year, but is ongoing, where the American Physical Society arranges for virtual classroom visits, because the other thing teachers asked for was better connections to quantum professionals. So they want to do activity, some of them want to develop full-scale curriculum, but then they want to make sure their students are learning or hearing from professionals. And we heard about this, I think, in one of the last two talks, or both of them, about how it's important to hear about mentors. And so Quantum to Go is a vehicle that we partner with APS to develop and then deploy for virtual classroom visits of quantum professionals. And we do this because we think it's really important to not just think about the pathway, but think about how students see themselves in those careers, and want to make sure that we have role models for them, because I think it's one thing to be really interested, but we're still trying to figure out, well, how do we help students every step of the way in this area where they may have never heard about it, or they've only heard about it on TV. And so trying to make it real by having role models, I think, is really critical. Okay, so looking ahead, we have a bunch of things we want to do. This initiative is pretty young. I would say, again, quantum education is young. When I get asked about success, I said this already, success to me is when every student in high school knows the word quantum and knows there's opportunity for them in the future. And so it's really kind of that level of public awareness. And then I think it's also a measure of success is when we stop calling it quantum education. So I think we're a ways away from that. These initiatives, similar to computer science, they take decades to move things along. So, our goal is to help accelerate that a little bit. And so we would really like to work in chemistry spaces to expand our footprint in the other subjects, and just continuing to support this community. And to that end, we would like to know, what are the roadblocks for bringing new science topics like quantum education in the classroom. I know the day is full. I know this topic is abstract, but I think we're learning there are ways to scaffold, starting in younger grades, the concepts, and think about it just as the way, another part of nature that students get to learn about. And then what resources do you need to support teacher readiness? And with that, I'll stop, and thank you so much.
Thank you, Emily.